The truth always turns out to be simpler than you thought. Richard P. Feynman. This video presents the elastic collision of two balls moving in opposite directions. In the absolute frame, two balls, one with mass m1 traveling at velocity v1, and the other with mass m2 traveling at velocity v2, are engaged in a frontal elastic collision, as shown in the figure. The velocities of the balls after collision are v1 prime and v2 prime, respectively. The equations for the law of conservation of momentum and energy of the balls before and after collision are equations 1 and 2, respectively. The two equations yield the solution for speed v1 prime and v2 prime, respectively. For m1, much greater than m2, the simplified solution v1 prime is approximately equal to v1, and v2 prime is approximately equal to 2v1 minus v2. The solutions are offered without considering the direction of the velocities. Considering the direction of v1 positive, the direction of v2 is negative, and the directions of v1 prime and v2 prime are positive, as shown in the figure. Therefore, the simplified solutions with approximation become v1 prime is approximately equal to v1, and v2 prime is approximately equal to v2 plus 2v1. At the limit when m2 converges to 0, the simplified solutions give v1 prime equals v1 and equation 3, v2 prime equals v2 plus 2 times v1. When the ball of mass m1 travels in the opposite direction, the simplified solutions are v1 prime equals v1 and v2 prime equals v2 minus 2 times v1 for the same positive direction. The massless balls obey the conservation law of momentum. m1v1 equals m1v1 prime, equation 1, and the conservation law of energy. 1/2 of m1v1 square equals 1/2 of m1v1 prime square, equation 2. According to the equations of these two laws, massless balls do not have momentum, and no energy is required to change their state. A wall W can replace the ball of mass m1 to study the reflection of massless balls in any direction, as in the figure. the mass of the wall can be ignored when studying massless balls. Equation 3 is given the frame at absolute rest, indicating that V2 adds once to V2 prime and V1 twice. In the wall's inertial frame, the instant speed of the massless ball relative to the wall is VII equals V2 plus VI, where VI is the speed of the wall in the opposite direction of the incident velocity, V2. In the figure, VI equals V1. The speed of the reflected massless ball is VRI equals VII equals V2 plus VI. Velocities VRI and VII are in opposite directions and equal in magnitude. In the frame at absolute rest, the speed of the reflected massless balls is V2 prime equals VRI plus VR, where VR is the speed of the wall in the direction of the reflected massless ball. In the figure, VR equals V1. The expression V2 prime equals VRI plus VR, where VRI equals V2 plus VI yields equation 4. V2 prime equals V2 plus VI plus VR. That is a comprehensive form of equation 3. Equation 4 offers the meaning of velocities VI and VR and provides the massless ball speeds reflected in the absolute frame V2 prime, where V2 is the emitted velocity of a massless ball by a source at rest in the absolute frame, coming from any direction to the wall. The wall may have inclinations other than 90 degrees from the velocity v. In this case, the angles of the incident speed vi and the reflected speed vr measured from the velocity v are different from 0 degrees. Therefore, the magnitudes of velocities vi and vr are different from v1 of the figure. Equation 4 applies to the reflection of hypothetical massless balls and light by a moving wall or mirror, and with approximation to the reflection of balls with mass by a moving wall in an elastic collision when the mass of the wall is much greater than the mass of the ball.